All right, so let's start out by looking at this problem right here. So we've got a physical pendulum, because it's not just a simple pendulum, we've got this whole rod here. And so to start off with, we can identify that we have a center of mass right at this location, and we have an axis of rotation up here at the top. So when we're measuring distance to the center of mass, we're going to use this distance right here as our value for d distance, and that's something we can keep in mind. So if you recall, we had an expression for the torque, which was mgd sine theta, or you can replace sine theta with just theta if you're using a small angle approximation, which we will be doing here. And then to figure out the rotational inertia for this entire object here, we're going to have to go ahead and use the parallel axis theorem. So remember for that, I center of mass plus the squared. And in case you forgot, we've got over here the rotational inertia for a rod about its center of mass. Then once you're done, hopefully you should be able to figure out the period of a simple pendulum very quickly and compare the two in that way. You can look back at your notes if you don't remember that one, or derive it from the equation. All right, so let's look at number 2 here. This one has two gliders set in motion. They're both moving at the beginning. You can see they're both moving to the right, but the second one is moving faster, so it's eventually going to catch up and compress this spring inwards to a shorter distance. And so we're kind of trying to look at what common speed the two gliders have when the spring is at maximum compression. And so keep in mind, while this back one is moving faster, that means that it's getting closer and more compressed until they're both going at the same speed. And then after they're both going at the same speed, the front one is going to start getting ahead. The back one is not going to be moving as quickly, and they will be uncompressing at that point. So the thing that we're looking for here is the same speed afterwards. And the approach we can take for this is one of momentum. Look at their initial momentums, look at their final momentums, and say that they're equal, and you know that both v final 1 and 2 are equal. So this will look very similar to an inelastic collision problem, but it's not truly an inelastic collision, but it's kind of like one. Then at the same time, we're going to find what the maximum spring compression distance is, and for that we're going to say that the change in energy is 0. So we're using conservation of energy for that. So you can see how much kinetic energy you have here, and the rest of it should be in spring potential energy. Okay, we can use that to find our distance. Now we've got our last two parts. Here is find the energy of the center of mass motion. For this, you can just pretend like you've got one mass that's all moving together with this common speed that you found in part A, and then to find the energy of the oscillation, that's just sort of is going to depend on the total energy at the beginning, because there's no friction, there's no energy loss here. So once again, we're just going to be using conservation of energy again for this next part. All right, moving on. I really like this question. We've got a block on top of another block. Block B is on top of block P. Don't know why they named them those, but hey. So let's think about the force diagram on block B. Block B has a weight, normal force, and some sort of friction. The friction is either going to be pointing to the left or the right, and it's going to be a static friction because the two blocks aren't sliding across one another. So with this sort of static friction, this is the net force. This is the force that causes the object to accelerate. And so because of that, there's actually is a maximum friction force. Just like always, static has a maximum value. Figure out what that is, then you can figure out what the maximum acceleration is, and from that you should be able to figure out what the maximum amplitude is. Because remember, there's a relationship between each of these. It has something to do with some A's and omegas or something like that. I'm sure you can figure that out. If not, again, please feel free to reach out and ask questions about these. Now, this last one, this is a rather complicated question. So here's what we're going to look at. We've got this block here, and hopefully you can write out the equations of motion for this block, the Newton's second law pair for this block. And that's what we're going to need to do overall to get this answer. So what I'm going to say is I've got this block right here. There are two forces acting on it. We've got a downwards mg and an upwards tension. And I'm going to call this tension 1 right here. And that's going to be equal to ma, little m, times its acceleration. Okay, then we can write an equation for the pulley. And remember now, this is a mass-full pulley, not a massless pulley. So when we write this one down, we've got to include the torques in each direction. And we're now using a rotational analog of Newton's second law. So follow along with me here. We've got that the net torque is equal to this. So we've got both tensions, they're pointing in opposite directions, hence different signs. I wanted to make sure that my direction of acceleration and my direction of angular acceleration both increased in the same direction, so that's why I have this as in the positive direction and this as in the negative direction in this case. Now, if we combine both these equations together, we can go ahead and solve for everything, but we really have some unknowns here in the case of what's T1, what's all the other ones. So you can start combining these, but the one big relationship you need to know and remember is that alpha times r is equal to the acceleration. In this case, it's capital R, but yes, basically this relationship right here. And so you can go ahead and replace this alpha with a over r. Go ahead and replace this with values that we know because it's a solid disk, so you've got values for that. We don't know numbers for either of these tensions, but we know basically everything else in all of these equations. And since we have so many equations, we can actually find some of these values out, or at least combine them in such a way that we don't have to deal with them. So actually, we're not finding out the values here, but we are going to get rid of T1 because it shows up in two of the equations, so we can get rid of those. And this one, T2, is actually equal to the spring force because the spring is attached to the end of the string. So T2 is going to be equal to just Kx. And so here we've got an equation that depends on x, something depends on a, and if we can write it in a form that looks something like this, then we know we have simple harmonic motion. Whatever term we have here in front of the negative that's squared, other than this x, or if it's not squared, then you'll take the square root of it to figure out what omega is. And this is sort of the approach to figure out the angular frequency. Now, it should be in terms of capital M, which of course is inside of this term right here, mr squared, 1/2. Mr squared is our rotational inertia. And so there should be an m somewhere inside of this value of omega, and this should be a symbolic answer for this problem. Now, you don't need to get part A in order to get parts B and C. For parts B and C, you're basically, one way you could do it is look at this equation and think about just plug in for omega, or for m, capital M as a variable, large numbers, small numbers, until you find something that's right. It's kind of like the limit of this equation. But the other thing you'd think about is, would the angular frequency increase or decrease if the mass of this pulley was larger? Would it increase or decrease if the radius of the pulley was doubled? And how would this affect each of those things? So I think that in most cases it would make sense that you would get a maximum angular frequency when capital M is either equal to 0 or equal to infinity. So you can kind of compare those examples and see what it looks like, and then you might be able to solve it with M equal to one of those values, even without going for A. So then you actually have numerical values for everything, and it's not a symbolic answer anymore. So these ones actually both have numerical answers in each case. And then think about what would happen when you go through this work. If M is also equal to 0 or infinity, how would changing the radius of the pulley have any effect, if at all? So hopefully that helps you get started. Feel free to ask any questions if you got them. See you in class.